All right, thanks everybody for coming here to see this presentation. So QUBO.jl is a Julia package for, not only a package, but an ecosystem for quadratic unconstrained binary optimization, which is basically optimization binary variables to have no constraints and a quadratic objective, so very simple model. All right, so let's start with the long story short. I was working at PSR quite a couple of years ago when I joined there. The question we were asking ourselves was, how can we integrate quantum and other physics-inspired technologies into regular optimization workflows? So very interesting things happening. New technologies have been developed for tackling and addressing some specific types of optimization problems, and this includes QUBO and some slight variations of it. And we want to know how to use these things and how can we apply this in our daily basis work. So our ideal dream was, how can we take this model that someone wrote 20 years ago, and we want to run directly in this new hardware that people just developed. So the first things we needed to accomplish this task was to access those solvers and to reformulate the models. Because as we were saying, it's hard to build this kind of machine, so usually you only have binary variables because it's the simplest form. You can see, so you have two states, also quadratic terms, just because linear is too easy, and then quadratic is what's accomplishable, because if you try to get three things together to get those cubic terms, it gets too hard. And no constraints also to keep it simple. So we need to reformulate models to fit in this kind of hardware. So to access the solver, the question is how to deal with so many different ways across all devices, and then so as to have a common interface for them. On the other side, to reformulate models, we want to do this without having to train people to do it. So we want to do these things automatically. And this brings us to develop a compiler for mathematical programming. So these were the two main tasks we had when we started working in this project. And after you have a common interface and you can connect to the solver, you want to pick the right solver, and this brings us to some benchmarking ideas. Also, we want to see how these things evolve, because technologies change, new solvers appear. We want to keep track of this very dynamic environment. And then we need a benchmarking library. On the other side, we want to choose the best way to reformulate a problem, because there are many ways to do so, and this leads to some architecture-specific compilation of those problems and goes back to benchmarking again. So in the end, we hope to arrive at these three products, so to say, and we are going to discuss how we arrive in that. So our main idea was to connect the industrial applications where you have some MI/NLP problem and make it fit in QUBO solvers. And the bridge to do this thing is to develop this software stack so we can get there. So an overview of the things that we have, something on the other side, we have the solver and the service architecture and some specific conventions. So on the top, we are talking about software, and on the bottom, we're talking about mathematics. And basically, we came up with this QUBO drivers package that allows us to very rapidly deploy jump interfaces, given the assumption that our mathematical model is very simple. So this package, you have a specialized macro that you say the name of your solver, some attributes, and you define this sample function that allows you to directly interface with the solver and get the results back. On the other side, we had the QUBO. That is this compiler that will translate whatever you have on this side into the QUBO formalism. In this side of the drivers we are talking about, we have a very heterogeneous solver landscape, which means that any of them will have a different API, will have some different but compatible mathematical framework. Some of them will be accessible locally, some of them will be photonic devices, quantum devices, others will be digital and be accessible through the cloud. So we gather everything through JUMP, so the user has this common interface to deal with them. And that's it. We deploy this using Julia packages, so you can access D-Wave, Qiskit Opt, which is IBM's optimization suite. You also have the NASA parallel tempering code, and all of them, you write the same code. If it's a QUBO model, it will run. And this was quite a nice achievement, because if you look at the documentation for those services, usually you need to be aware of how they represent things. Some of them like the matrix to be symmetric, some triangular superior, and this gets very messy very fast. After we had a way to access the solver, some natural thing that came after it was to have some way to benchmark them, assuming that they are all connected to jump. So a big problem in this community when you talk about physics-inspired and these novel heuristics for solving this kind of problems is that each hardware manufacturer or algorithm developer, they will select some problems that run better on their hardware, and they put out a paper. And what we want with QUBOWL is basically to deploy a service that is available online, where all the solvers are integrated to jump, and this benchmark is run continuously. So you can see how different versions they evolve, and you also set a common ground. So in our dream is one day people will arrive at one of those conferences, and there will be a running monitor there showing the latest results, and people will be able, oh, no, I have some better algorithm now, and this change in real time, and that's a way to set these milestones. But also it has another side, which is how to measure these things, because it's already hard to compare when somebody runs something on the CPU and GPU, and imagine now I'm running something on like super cool down silicon or superconductor, these kind of things. How we measure it's the energy I spend, it's the time, so there is also some work in this sense behind what you see in QUBOWL. So QUBOWL, essentially, it is a collection of other well-known quadratic programming, and especially quadratic unconstrained binary programming. We gather them together. We also use our reformulator to generate some of these instances. So, and everything that we have here is indexed by a SQL database that allows you to select which kind of instances you want. So in this example, what we see is that we are filtering by the dimension and the quadratic density, so we can better see what we run. In the same way, the results are made available the same way, so you can conduct like further analysis after that. If you want to know more about this, specifically about the benchmarking part, I'll be talking about it in depth in ISMP in 2 days, Monday afternoon. Yeah. All right. So when you talk about the compiler for the mathematical programming, what we usually see in the literature is a very straightforward process. So we take our original model, we encode our variables, so they become all binary. Later, we penalize the constraints, we move them to the objective, adding some kind of weights to them. Then we have this pseudo-Boolean mapping, which is basically a reinterpretation of what we had before that allows us to write everything as polynomials. This is what the theory gives us. And since this can be a higher order polynomial, we have to reduce it through a process called quantization. So this is what you find in literature, usually, very straightforward. This is what was implemented into QUBO. And this is very similar to what you're doing when you're trying to compile some kind of higher level language into some lower level one. We can imagine that QUBO is the equivalent to what assembly would be to most of these machines. They are very close. They have the specificity. Sometimes you have to do a further step to make it fit in the hardware, but it's usually the closer you can get to controlling what's happening. And in the same way, you have some intermediate language where you can conduct optimizations. In your model, you can derive bounds. You can get better formulations in the middle of the way. So here, pseudo-Boolean functions, they have a very important role. And basically, everything boils down to them before reaching the QUBO format. All right. So for those who are new to the package and how it works, we have some example. And so since everything starts with power systems, we have some generation capacity expansion. We have some facilities that we have already built, and we want to operate with them, but we have some candidates in which we can build or not to allow our operation. So here we have the model, the operation, and the balance are represented here. We have to fulfill that demand. We also have some choice, which is a continuous variable, something that we don't have natively in QUBO. We have the unique commitment constraints, and we also have the investment constraints and the investment in the objective. So if we were to translate this directly into QUBO, what we have to do is take everything in the model, and we have to penalize it in a certain way. The variables have to be encoded using binary ones, as we can see here. So this whole thing is to just show how, if you're going to do this manually, this can get very annoying very fast and prone to errors. So instead, you can just take some of our well-known jump code, where you can see the constraints and variables are all represented there. The continuous ones, they are given as is. And all you have to do is to wrap your solver. So PySA is parallel tempering code that basically solves QUBO. And it's not compatible with the original model, but as soon as you wrap it with the QUBO optimizer, it's just ready to go. And the results that you see below, they are retrieved in the original frame of the user. So from a user standpoint, you're just dealing with a regular solver. All right, so talking about some of the results, we expanded a little bit. The others that we benchmark here is just the reformulation performance. So ours is the golden one below everybody. So here is in log scale, the time it takes to reformulate a problem given the size. And these two others that are closer to ours are also C++ code. The others behind are Python code. And we outperform them both in the scaling that we can see in a problem like the traveling salesperson, where the number of constraints and variables, they do not grow linearly as in the number partitioning, where there are no constraints. It's basically a QUBO from scratch. So we are beating them both in scaling and in the offset baseline. It's the fastest reformulator you can find out there. All right, there's a more qualitative analysis, which is basically which is the coverage of our solver in which kinds of constraints and techniques it implements. And just recently, some other group showed up with this comparison that extends the one that we presented 2 JuliaCons ago. And what we see is that they are claiming that they outperform our solver in terms of coverage. So this is very exciting, actually, because you now see there's like new people in town, and we want to like catch up with this. But some of the things we're going to present today, they in fact expand our capabilities, and it will be nice to see how it looks shortly after we account for these new features. So basically, what also they show, that's our column, is that we are also outperforming the other competitors, as we have shown in the paper that we put out, but now we have new targets. And also there are some techniques that we implement that are not even considered in this table, so it's worth checking the original paper. All right, so what I have new is that from the previous presentation about QUBO specifically, is that besides aggregating everything in this QUBO.jl ecosystem that integrates all these small packages that do reformulation, the connection with the solvers, we now have some new features on top that help also the user experience. So QUBO and QUBO drivers, they operate at a MOI level, and QUBO provides the full jump integration experience. So you just, usually the user is concerned about just using QUBO, while before, if you want to extend it, you are going to import the QUBO and QUBO drivers. So what's new from the previous presentation is that we have some additional attributes that help you control what's going on, so you can select how your variables are going to be encoded. You can give hints on the penalty, so the software doesn't need to figure it automatically. You also have reformulation callbacks, which is an interesting way to give the user control of what's going on. So every time it has some constraint to process, the user can say, oh, I know how to do this more efficiently. And this was particularly useful when implementing the disjunctive programming you're going to talk in later. And the architecture-based dispatch allows you to override and overload some of the functions that will process those constraints and variables to account for particularities of your hardware. So depending on the solver that you're using, this is also something you can dispatch on like readily. So if you know that your hardware responds to some better technique of encoding, you can just say, oh, stop here, and I'm just taking control and doing this different stuff. And it was nice that Josh's presentation was today, because from what we presented recently was this extension called disjunctive to QUBO that leverages everything that was done in disjunctive programming and allows for this integration, and especially taking some of the semantics of the disjunctive programming into account. So instead of going all the way from the MNLP and going through the MIP reformulations to then arriving to QUBO, we figured out that there are some ways in which you can directly reformulate from indicator constraints into QUBO and take advantage of these logical relations. All right. So this was what happened in the only QUBO part, but also there are some QUMO solvers around. And the last 3 months, I spent doing some work with them. And QUMOs, they are basically QUBO problems, but they have this extension that allows you to encode also continuous variables natively. So we are interested in integrating them as we did for the other kinds of hardware. So the ones that support this are this lab at Microsoft Research, where I spent the last 3 months working with. And as we can see, the only difference in the formulation at all is that you now have these new variables enclosed in a closed interval. And what we see is that QUMO is a small extension to the QUBO things, and we thought in the first place that, oh, it's going to be very straightforward. We just use all the machinery we have already. But unfortunately, the pseudo-Boolean theory doesn't apply the same way as we were expecting before. So in a certain sense, we had to rethink much of the pipeline that we were working. Oh, so David just arrived. That's great. So you have to rethink much of what we were doing before, because we were assuming that everything was going to reach the pseudo-Boolean function level at some point. And then we could just follow from there, and now this is not true anymore. So a lot of the pipeline had to be thought again. So to do this, we had great inspiration on the MOI bridges, and how they are done were an invaluable resource to arrive there. And the way that we are approaching this is basically to take the source model and you look at which variables and objectives and constraints are accepted by the target model and which are not. So in this case, we can see that inequalities are not supported because we do not allow any constraints. So what we're going to do is have this slack variable transformation where we add some slack variable, we include it there. But now we have some equality, which is still a constraint. We have to penalize it, and we have to take care also of the slack variable over there. So in the end, we aggregate the objectives we have, and the slack variable, it doesn't have a upper bound. We have to estimate it. So the process would go something like this. We have a priority in which we process things, and this is something very important that is kind of missing in the QUBO reformulation literature, where you look at your variables, then you usually look at your objective, look at your constraint, and here it's important to process the variables, you know what they are, but then you try processing the constraints first, because sometimes they will give you information on how to encode your variables. So usually you follow this order where you want to process the constraints first and generate objectives, and in the end you're going to encode your variables and take care of substitutions. And this is important to come up with more clever tricks that we talk in other works. related to this. So in the end, we just write the model. So what about the MOI bridges and why didn't we use them? So the first thing we thought when we just started working with this was, okay, let's use MOI bridges and put new bridges to do these things. And in fact, if we look at this one here that creates this slack variable, this could have been done by MOI. And it's great to be able to leverage these things and just use them right away. But it happens that some of the operations we are doing, they are too destructive. So currently, MOI bridges, they do not natively allow you to transform a constraint into an objective and keep track of these things. So we have to take care of some of these transformations by ourselves, because also when we are encoding variables like continuous into discrete ones, we are losing information, and the relations, they are not equivalent anymore. We also want to play a little bit with the pathfinding algorithm, and yet bridges, they do support you setting the weight, so you can find more clever paths. But we want to have control not only on the type, but also sometimes it's dependent on the data that we have inside each one of the nodes. So we want to have some more fine-grained control over these steps. But as we showed here, for those who are familiar with the bridge systems, it's very, very similar to what's going there, and it was a great inspiration for this new iteration that accounts for the QUBO formulations. All right. So the next steps would be to generalize this whole reformulation algorithm, because you can parameterize this in such a way that if you have one that's capable of reformulation for QUBO, and you just say it doesn't support continuous variables, but if you want to discretize them, you can arrive at good QUBO formulations, and the algorithm is quite similar. So this could be a natural way to expand the whole project. We want naturally to expand the constraint support to catch up with the new competitors that we showed up there, and also to account for some constraints that are relevant for the applications we're interested into. And we want to set up this continuous benchmark services that I was talking before, and use this to draw insights to guide the reformulation. So these weights that we have in bridges, we could use the results that we get from the benchmarking, knowing which kinds of constraints we have and what are we generating of kind of code, and use this to select the best path. All right, and from the time that I spent there working with this new machine, there was some ideas about things that would be nice to have in JUMP. So this is just some food for thought, maybe for ideas for the hackathon tomorrow, is that they're setting up this LED. It's a machine that works using light to compute and to solve these optimization problems. And it's something that you need to have inside the lab, but you want to deploy this using a cloud service. And in fact, this is true for other services such as the one that IBM has and other companies. So it's interesting if we had some way to access this asynchronously, because most of them will place your request for a solution in some kind of job queue that you want to access later through futures. And usually if you implement some kind of interface through optimize, it will get stuck, and you need to wait until the completion. But sometimes you want just to launch a lot of jobs, and you want to return this as futures that you can access later. So people were talking, and they were interested in knowing more about how could we have this interfaces for doing optimization over this kind of requests. And this is also interesting to set up different services that rely on optimization. So you could begin writing some kind of client-server applications, and this leads to thinking about an interesting communication protocol for sending models and retrieving, which is a struggle when you think of all these machines people have been developing. A lot of them will ask you for file formats or ways of submitting problems that are very, very impractical. So they expect you to upload huge files into the cloud, and this is something that's interesting to think in terms of what MathOpt interface has already provided in terms of file formats and ways to write models. So thinking about how to communicate these things would be something interesting too. All right, so I would like to thank very much to the team that has been working with me all this time. So thanks Joaquin that's here, and also David that's here, and Pedro and Nelson who are not here but were invaluable to the completion of this project. And also thanks my colleagues at Microsoft recently, Christos and Kirill, that were amazing into participating and are very enthusiastic about the Julia and the Jump community, and developing more to enhance the ecosystem as a whole. All right, thank you.